So, okay, visual examples, just so we're there. So we've got 500 nodes, and this is using, I should try NetworkX or something for this. This is an old one. So let's see, so 500, we're gonna vary m, number of edges from 100 to 1,000, so 2 times m divided by n, right? That's our little simple calculation, right? Average degree, wow, dead. Also dead. Average degree is 2m over n. So, yes, we go from 100 to 1,000, so we're gonna double this thing. So it's going to be 200 over 500, 2,000 over 500. So we're going to have an average degree going from 0.4 to 4. And as you may recall, if you've been in pucks before, 1 is the big deal here, right, for random networks. So it's a good anchoring. So we're going to look at the full network plus the largest component. So this is sweeping across these average degrees. So again, 0.4. Tightening up around 1, just because there's more interesting stuff there, 0.8, 0.92, 0.96, and this is 1. Of course, there's just one instance for each of these, and it's only 500, but which is not a lot of, it's not a big network by any stretch of the imagination. Let's see. So you see, a lot of isolates here, right? So nodes that have no friends, and then these are all little pairs. And then there are a couple of triples in here. This one looks like it's 1, 2, 3, 4, 5. So that's the biggest one in there. Certainly no cycles. Right? You could have some with some randomness, but no cycles here. So you start to get these tree-like structures connecting, and for random networks, the key thing for a lot of the analytics will be that locally everything is a branching network structure. So even though as we get to hairballs, it's still going to be all about branching network structures. All right, which is quite fantastic. Calculations are really beautiful. We will get to generating functions, which will warm everyone's heart. It is quite majestic. And has power, but you don't have to use it everywhere. Okay, so let's see. So we get to here, and this is an interesting case. It's starting to get a little nutty, and that's certainly true here. And we're only a little bit above 1. Again, 1 instance. But the singletons are dying out, right? The number of nodes that just have 1 friend. There are just a few of them sort of scattered here. Right, so a big issue is how do you display these things which are obviously much higher dimensions and higher dimensional structures in 2 dimensions. And that is, always a bit of a game, but this is just sort of smushed. Do you get this sort of? Yeah, at some point. Yes, and there's some really nice transitions in terms of when you get giant components. All those things are there too, right? So you get the same kind of story, like whether the realized one will have a giant component. And we have to think about the things we're trying to create. But usually you're inducing the network, right? So there are these 2 groups, and they, what we're going to do is project, right? So if you share a category, then you're friends, right? So we'll do that sort of thing. The really interesting things to play around with there are just like moving it a little bit, where you fill in the network a little bit. You sort of say, you start to add some extra connections, and that changes everything. But just small deviations away from these models are quite valuable. But let's see. I know you've asked probably not what I've. Yeah. We'll get to that one. And maybe I should make some pictures for it. Yes. Okay. Okay, so these are the largest components. So this one had 7 in it, and again, it's just a random instance of it. And we start to see a loop here. That seems to have sort of disappeared in this one, but which is we didn't see one in this example. Loops, loops, loops. And the loops are long, right? So they're relatively long. Again, not a very big network in the first place, but there aren't any triangles here, right? Because that's going to be a harder thing to get out of just a random wiring. And we really have, by even just an average degree of 4, this is really an important thing to sort of understand. The average degree of 4, which is not many, we've certainly got a hairball, right? Which is a mess to try and put onto a page at this point. This one, we could imagine trying to tease it apart, but nasty. So average degree of 4 is pretty rough. All right. So that's the largest component. But this is just the sort of, this is an entry into thinking about things like disease spreading and so on. There can be a dynamic underneath how these networks are created, or you might be looking at an outbreak after the fact, and this is something where it went kablooey, right? This is bad. Yeah. If you have some way of controlling connections, like how people interact, then you want the big deal will be to move the system below this 1 here, because now you do not have a giant component, right? So we'll talk about a giant component. That means the largest connected group in the subnetwork, and it will be giant if we can see it from space, basically, right? So if it takes up a macroscopic fraction of the whole network. All right. So these are just a whole bunch now for just average degree 1, right? So this is a critical point for this system. Critical points are fickle things, especially at low numbers. If we took it to an infinite limit, they would all do the same thing. But at 1, you get this kind of, the largest component tends to be a fractally, tendrily thing. Is that on the next one? Yeah. So it tends to be, and this is true of percolation type things, all sorts of other structures where at the critical point you tend to get a sort of a fractal thing. It doesn't take up the whole space. Yeah, so spidery, webbery things. And then, right, as soon as we sort of move above, right, we tune it so the average degree is a little bit higher, then we'll start to see these loops. I mean, we'll see some, of course, anyway, but this is, again, a finite size effect. Okay, it's sort of a feel for these things.